Welcome back to my video tutorials of computer organization and architecture. This video is about multiplication of positive numbers. Product of two n-bit numbers is at most a 2n-bit number. Here this indicates 4-bit multiplicand and multiplier is also 4-bit in length and the product is 8 bits in length. Okay, what's the meaning? While multiplying two n-bit numbers and the result, the product value should be less than or equal to 2 into n bits in natural. Unsigned multiplication can be viewed as an addition of shifted version of the multiplicand. Here, while multiplying this multiplicand with this last bit of multiplier, we want to write down the multiplicand just down without any shift. While multiplying the same multiplicand with the second bit, what happened? We want to shift one bit left, then write down the multiplicand just down after this step. Okay, while multiplying with a 0, we want to shift 2 bit left, then write full of 4 zeros here. Then while multiplying the multiplicand with the last bit of this multiplier, what happened? Shift 3 bit left, then write the multiplicand directly down. Then add column wise, add values column wise and generate the final product value. Okay, so each step for each multiplication of the multiplier bit, we want to perform suitable left shift operation. With the proper left shift, we want to write down various partial product value. While multiplying with 1, we want to write down the multiplicand itself with proper left shift. While multiplying with 0, we want to write full of zeros with proper left shift. Okay, and we added the partial product at the end in normal cases. This is the normal way of multiplication. Here we generate different partial product value and at the end we add column wise different partial product values and generate the final product of multiplication. Alternative method of multiplication is add the partial product at each stage, just like this. Okay, here we have the same multiplicand and multiplier, both are of length 4. So consider initial partial product of 4 zeros. Okay, so while multiplying the multiplicand with the last bit 1, generate a value 1101 1101 and add this value with the previous partial product value 0000. So while adding with 0, generate a new partial product value PP1 as 1101 itself, that is the multiplicand value itself. So just write down this PP1 value here. Okay, next multiplying with the second 1 bit of multiplier. While multiplying with 1, we want to write the multiplicand itself with proper left shift. But here we want to perform an addition operation of the multiplicand with the previous partial product value. The previous partial product value here is 1101 1101 and the new intermediate multiplication result while multiplying with this 1 is 1101. So perform 1 bit left shift and write down this intermediate multiplication result. Then perform an addition with the previous partial product value and generate a new partial product value at the second level is 111001 here. So this is the partial product at stage 2. Okay, 100111. Okay, here 1, just write down this 1, 0 plus 1 1, 1 plus 0 1, 1 plus 1 0 carry 1. The 1 inside the circle indicate carry from the previous column. Okay, and this 0 indicate the sign and extension of this partial product. Why the 0 as sign extension? Because both the multiplicand and multiplier are positive number. So each partial product value should be positive. So the sign and extension should be 0 in each of the partial product cases. Okay. So here add this 1 plus sign extension 0 plus the carry value 1 and generate 0 carry 1. So just write down this carry here. Okay, so while multiplying with the third 0 bit, we want to perform 2-bit left shift. Then write down full of 4 zeros here, because here we are multiplying the multiplicand with the third bit of multiplier. The third bit of multiplier here is 0. Okay, while multiplying with 0, no need to consider the multiplicand. We just want to write full of zeros. Okay, then perform the addition with the partial product. Previous partial product value. So just write down this 1 here, next one here, 1 plus 0 1, 0 plus 0 0, 0 plus 0 0, 1 plus 0 1 here. Okay. Next, so the partial product at level 3 is 1 0 0 1 1 1, 1 0 0 1 1 1. So while multiplying the multiplicand with the fourth bit of multiplier, the fourth bit of multiplier here is 1. So want to write down the multiplicand itself. But we need to perform 3-bit left shift before addition. So perform 3-bit left shift, then write the multiplicand here. Then perform the addition with previous partial product value. 1 here, 1 here, 1 here. Sorry. 0 plus 1, 1, 0 plus 0, 0, 1 plus 1, 0, carry 1. The 1 inside the circle indicate carry from the previous column. This 0 indicate the sign extension of this partial product. This partial product is positive always, because both the multiplicand and multiplier are of positive. So we need to consider the sign extension of this partial product as 0. So while adding this carry 1 plus 0 plus 1, generate a result 0 carry 1. So consider both the result are same. So we have two different method for multiplication. One is add all the partial product at the end, or add the partial product with the new value at each stage. Okay, both method generate the same result. Okay, so this indicate implementation of two-dimensional array implementation of positive multiplication. Here we use combinational arrays, combinational two-dimensional logic arrays for implementing multiplication. Okay, this M0, M1, M2, M3 indicate different bits of multiplicand. Similarly, Q0, Q1, Q2, Q3, etc. represent multiplier bits. Okay, and initially the partial product value PP0 is initialized with 400. Okay, and at each row indicate the result of or partial product value while multiplying with a different multiplier bit. This indicate the partial product obtained while multiplying with the LSB bit of multiplier and the multiplicand. Okay, here initial carry value is considered as 0. So after the first multiplication Q0 plus Q0 and M0, multiplication of Q0 and M0, the carry out is passed to next level. Here we want to perform Q0 into M1 and then want to add the previous carry value as well as the previous partial product value. Then generate new partial product here and is passed to next level. Okay, here the cell perform first a multiplication with Q0 and M2 and perform an addition with the previous partial product bit value with the carry from this particular cell. Okay, the same operation repeated in all the cells. And finally, generate a partial product of partial product value here is P7, P6, P5, P4, P3, P2, P1 and P0. 8 bit in length, because both multiplier and multiplicand are 4 bits in length and generate 8 bits. Okay. So here each cell perform a multiplication and AND operation, then perform an addition of previous partial bit value with the result of AND operation and the carry in value. So each cell looks like this. Each cell consists of an AND gate. AND gate perform a logical AND operation with a particular multiplicand bit with a particular multiplier bit. And the result of this AND is added with partial product value from the previous level with the carry in value and generate the partial product value for the next generate a particular bit of the next level partial product value, as well as generate, carry out and pass to next cell in the same row. Okay. Multiplication is usually provided in the machine instruction set of a processor. Multiplication is directly implemented in the processor set itself. But the previous combinational multiplier uses many gates for multiplying numbers. Look at this diagram once more. Here we want to perform 4-bit multiplicand with 4-bit multiplier. In order to perform such multiplication, we need here 4 into 4, 16 different cells. And each cell consists of an AND gate and a full adder circuit. So, if we use this combinational multiplier, we need many number of cells in order to implement such a multiplication. So improve the gate efficiency by using a mixture of combinational array techniques and sequential techniques requiring less combinational logic. We can improve or we can reduce the number of gates, just like here we need large number of cells in order to implement a multiplication. As the number of bits in multiplicand and multiplier increases, number of cells required also increases, and each cell consists of full adder and AND logic. Okay. So in order to increase the efficiency or in order to reduce the number of cells used, we can mix the combinational array techniques with sequential techniques. Okay. So this is the principle for performing a sequential multiplication. What's the principle? Here we have 4 different arrays. M indicate multiplicand array, A indicate accumulator array, Q indicate the multiplier array and C indicate carry bit. At the start, the multiplier is loaded into register Q and the multiplicand into register M. C and A are cleared to 0. Initially, multiplicand is loaded into this M array. Accumulator is initially set with full of zeros. This number indicate the number of bits present in multiplicand or in multiplier. Okay, and set this carry value initially as 0. And multiplier is loaded into array Q. Here 1011 is the multiplier and 1101 is the multiplicand. Okay. At the end of each cycle, C, A and Q are shifted right one position to allow for the growth of partial product. Here, we want to consider the least significant bit of this Q array. If it is 1, we want to perform an addition operation of current accumulator array with multiplicand array and just write down the values. Okay, if this current LSB bit of this Q array is 1, we want to add the accumulator array value, current accumulator array value with the multiplicand array and write the result in the accumulator itself. Okay, so just write down here Q, the LSB of Q is now 1. So we want to perform an add operation. So perform add 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 0, 1. So write the new added value back into the accumulator register, accumulator array itself. Okay, and just write down the carry value here, and similarly write down the Q value, Q array value just down here. Without any change, write down the Q value and C value just down here. Okay, then perform a shift operation, right shift operation. Perform 1 bit right shift. 1 bit right shift means just discard the last bit, this one. Okay, then this one comes here, this 0 comes here, this 1 comes here, and this one here, and 0 here, this 1 here, this 1 here, and this carry 0 here. Then put a new 0 here in the carry field. Okay, after addition, if the Q bit, the last bit in the Q array is 1, then perform an addition of accumulator array with the multiplicand, then just write down the value here. Okay, then perform a 1 bit right shift. This right shift operation is for just discarding the last bit of this Q array. Now the second bit of this Q array comes here in the LSB position. Okay, and new 0 is added in the carry. Okay, then repeat the same. Here the LSB bit contain 1 again. So if it is 1, we want to perform the addition again. Addition with the current value of accumulator with the multiplicand. The current value of accumulator is 0, 1, 1, 0 now. After the first shift operation, the accumulator value is modified as 0, 1, 1, 0. Okay, here now the LSB of Q array is 1 again. If it is 1, we want to perform the addition. So perform the current value of accumulator with the multiplicand. So 1 plus 0 equal to 1. 0 plus 1, 1. 1 plus 1, 0, carry 1, 1 plus 0 plus the previous carry 1. So 0 and the carry is loaded in C array. Okay. Then after the addition, we want to perform 1 bit right shift. So just discard this last one. Then this 0 comes here, this one comes here, this one comes here, and this one here, this one here, 0 here, 0 here, and this carry 1 comes here. Then put a new 0 in the carry field. Okay. So again go to the least significant bit of Q array. Now the LSB bit of Q array is 0. If the LSB bit of Q is 0, we don't want to add the accumulator array and the multiplicand array. The previous value of accumulator itself form the new partial product value. So just write down this previous partial product value which is present in the accumulator array 1001 here as the new partial product value. Why? Because here the LSB bit of this Q array is 0 now. If it is 0, just write down the accumulator array down as the new partial product value. If the LSB bit of Q array is 1, what we want to do? We want to add the current value of accumulator array with the multiplicand value and generate new partial product value which is loaded back into accumulator array. So here the LSB bit of Q is 0. No need to perform addition of accumulator and multiplier. Just write down the accumulator array value as the new partial product value. So just write down this value 1001 here. Carry value, write down again 1110. The Q array value just write down here. Then perform 1 bit right shift. So just discard this 0, 1 here, 1 comes here, this one comes here and this one here. 0 here, 0 here, 1 here and this carry 0 comes here. Then put a new 0 in the carry field. Okay, discard from the LSB bit of this Q and put new value in the carry field. So attach a new 0 in the carry field. Okay, so here it is 1 again. If the LSB bit of the Q is 1, what we want to do? We want to perform an addition. Addition between the current accumulator array value with the multiplicand value. Multiplicand value is 1101 and the current accumulator value is 0101. So after performing addition, the new accumulator value becomes 0001. Okay, with a carry value of 1 and the carry is loaded into C array. Okay, then just write down the Q values and perform 1 bit right shift operation. So discard this 1, then 1 comes here, this one comes here, this one comes here and this one here, this 0 here, this 0 here, this 0 here and this carry 1 comes here. Then put a 0 here. Okay, how many times we want to repeat the same procedure? Here we have 4 bit multiplicand and 4 bit multiplier. So repeat the same steps. Add, shift or no add shift operations 4 times. Hence the final result available in an array combination AQ. The result is available in AQ. So 10001111 is the final result, which is equivalent to 143. Okay, this is the sequential multiplication working principle. Consider the LSB bit of Q array and if it is 1, perform an addition of accumulator array with the multiplicand and load the result of addition back into accumulator array. Then perform 1 bit shift operation. After that, check again what is the new LSB bit of Q array. If it is 1 again, repeat the same. Add the accumulator array value with the multiplicand value and write the result of addition back into accumulator array. And perform 1 bit right shift operation. Okay, again check the LSB bit of Q array. If it is 0, no need to perform addition of accumulator and multiplicand. Just write down the previous accumulator value here. Okay, then perform again the 1 bit right shift of CAQ arrays. Repeat the same. How many times? Here we have 4 bit multiplicand, 4 bit multiplier. So repeat the operations or repeat the cycles 4 times and finally the array sequence AQ array combination generate the final product value. Okay, this diagram shows the sequential implementation of positive or unsigned multiplication. Here we have only a single adder and 3 different arrays. So perform the addition and shift operation or no addition and shift operation n times and generate the final product value using this single set of implementation. Okay, this is an n bit adder. This indicates the accumulator array, this indicates the carry array and this indicates the multiplier array and this indicates the M array, which is the multiplicand array. Okay, here we have a control sequencer or control logic. This logic check the LSB bit value of the multiplier. If it is 0, it perform and no add but one bit right shift operation. Then write the result back into this accumulator array. Okay, again check the LSB bit of this Q array. If it is 1, what do or what operation this control sequence activate? This control sequence command for an addition and 1 bit try shift operation. Then the adder perform the addition and write the result back into this accumulator array and perform 1 bit try shift operation. Repeat this procedures n number of times because both the multiplier and multiplicand are of n bit in length. So repeat the procedures n times, and finally this AQ array combination indicate the final product value. Okay, these are about multiplication of positive numbers. Thank you.